repetitive control system concepts and applications. And Dr. Eddie received the Bachelor of Engineering degree from Gajah Mada University, Yogyakarta, Indonesia in 2003, and a master degree from University of Adelaide, Australia in 2009, both in electrical and electronics engineering. He received a PhD degree in control system from Swinburne University of Technology, Hawthorne, Australia in 2013. He is currently a senior researcher and a group leader at Optoelectronics and Control Research Group, Research Center for Physics, Indonesian Institute of Sciences, Tangerang, Selatan, Indonesia. During his academic career, he spent some time as a visiting research fellow and at European Organization for Nuclear Research, 2014, Switzerland. Royal Melbourne Institute of Technology, 2015, Australia. Swinburne University of Technology, 2015, Australia. Technic University Berlin, 2015, Germany, and Northern Arizona University, 2018, USA. His research interests including learning control, robust control, adaptive control, speech recognition, image processing, machine learning. He has published more than 30 peer-reviewed articles in both journals and proceedings. He also serves as a reviewer of international journals such as IEEE Transactions on Industrial Electronics, etc. And now I would like to invite Eddie to give us, the presentation entitled Sliding Mode Repetitive Control System, Concepts and Applications. Thank you, Eddie. Welcome.
All right. Thank you, Wang.
Yep.
Then I would like to share my slide.
Yep.
Okay. Thank you. Good afternoon, everyone. So I hope that everyone is doing well in this current pandemics. And actually, right now I'm working from home because in my office, there's a policy that it's like a safe one week working from home and 1 week working from office. And to start with, first I would like to thank Dr. Hai Wang from Murdoch University for inviting me to give a talk in this seminar. Actually, it's such an honor to present in this seminar, a seminar by IEEE Industrial Electronics Society, chapter Western Australia, even though I myself is not an IEEE member. And my name is Eddie Kurniawan, and everyone can call me Eddie. I'm working on Indonesian Institute of Science here, so this is the institutions, and then in the Department of Research Center for Physics. Okay. My talk will title a Sliding Mode Repetitive Control System, Concepts and Applications. And my presentation material is composed of, first I would like to a brief overview about my institution, a research center and research group, and then after that a short introduction about digital control system, because most design is mostly done in discrete time, and then I would like to explain about the repetitive control, and then I would like to explain as well about the internal model design, and then I would cover a certain type of repetitive control called as high-order repetitive control systems. And number 6, actually, I would like to discuss how to integrate a repetitive control and sliding mode control system to get a better performance, and then I close with the conclusions. And this is my institution, named Indonesian Institute of Science. And the official name is actually LIPI. So it's not IIS, but it's LIPI. And the headquarters here is based in Jakarta. And this Indonesian Institute of Science has 25 research centers, 4 administrative bureaus, 4 botanical gardens. So we have a botanical garden as well, and there are about 1,000 and almost 1,600 researchers, and the 25 research centers are located in 11 provinces. So it's not all centralized in Jakarta, but in 11 provinces in Indonesia. And this Indonesian Institute of Science is the largest research institution in Indonesia, and it's also government research institutions, and it's established in 1967, and it's also rooted from colonial era in 1817 with the establishment of Center for Plant Conservation, and we are a leading patent contributor in Indonesia. That's about the Indonesian Institute of Science. And the next is that it's about the research center. So my position is as a senior researcher, also research group head, and the name of research group is Optoelectronics and Control. So we are doing research and development in optics and also control. And the department is Research Center for Physics. It's one of the research centers in Indonesian Institute of Science. And this research center is located in South Tangerang, so it's not in Jakarta. So it's a different province. The province is in Banten. And this research center for physics, has about 10 research groups. There are optoelectronics and control. So we have also laser group. We have lithium battery and supercapacitor group. We have high resistant materials, fuel cell materials, and hydrogen. Low dimension functional material, theoretical and computational material, complex system physics, theoretical high energy physics, nanomagnetic material. So the research group is actually expanding from theoretical until to applied physics. And how about the research activity in my group? So in my group, we are doing several research activities that we are developing, like autonomous drone and control. So we are trying to develop learning controls, both theory and applications. And we are developing as well a landslide monitoring system, because landslide is sometimes happen in Indonesia. Also, we are developing a weight in motion sensor to measure weight from the moving object. Also, we are developing a rain gauge calibrator. So this is some prototypes of our developments. Then, next is digital control systems. I would like to introduce first, because mostly my design is done in discrete times. Why digital control system? We have a digital control system here that the digital computer or controller is used to control plan, process, or plan or process. This double plan. And actually, this digital computer has control algorithms in the feedback control system, and the measurement data from the sensor is converted from analog to digital. And the digital computer processes the measurement data and provides control output in digital form. And the digital output is converted to analog to signal in order to drive the process. So, because at this time the digital control is pretty cheap, and that's why I would like to revisit the digital control configurations. And how to do conversion from the continuous to discrete time? From the usually in the first time is we know, or we have the model in continuous. For instance, this is the continuous model of servo motor. So this is the transfer function from voltage to the speeds, and this representation we can have, or we can change to state space model, and this state space model also in continuous times. But how to bring to in discrete times? So to bring in discrete times, for instance, we have this kind of state space. We have matrix, system matrix A, input matrix B, and then output matrix C, and this disturbance matrix D. And if we specify the sampling time t larger than 0, but it's pretty small, it's very small, then we can convert this state space continuous into state space discrete time with this function. So firstly, we have metric A, B, C, D, and then after that we'll have a metric G, H, C, and D, where metric G is a function of sampling time, and metric H is also a function of sampling time, while metric C and D is actually similar with the metrics in state space, continuous state space form. And how to obtain G and H? We have this function. And from state space to convert into transfer function, we have this equation. And from there, we can, from this plan model, discrete time plan model, we can design digital control systems. Next is the what's the time domain representation of digital control system. So actually in digital control system, we have a Z domain or frequency domain, and we have a transfer function in both a controller and plan process. So for the control, actually we are trying to generate the control signal UK, and as the function of the previous value of UK, and also the error. While for the plan, actually we are trying to generate the output here, plan output, also as the function of the previous value of YK, and also as the function of control signal, a previous control signal UK. This is just one example. So this is how we represent the digital control system in transfer function or in frequency and also in time domains. Next, we go to the repetitive control. I would like to introduce about the repetitive control. I think it's already well established since 1970. And repetitive control is basically a learning control schemes, but this learning control scheme is different like a neural network or AI. This learning control system is based using the previous value, one period value, and this RC is powerful for perfect reference tracking and also good disturbance rejections. And the requirement is that the reference and disturbance has to be periodic signal, and the application for the RC can be used for robot control. For instance, here is for pick and place robot doing repetition tasks, pick and place repetitively, and also used for hard drive in industrial machinery to remove the vibrational disturbance. Also, I think this is the early use of RC to provide a periodic current supply for proton synchrotron. So this proton synchrotron require a current in this form. It's periodic, and also it exhibit sub signals, and this RC can be used to do that. And this is another example. For instance, this is a 2 degree of freedom robots. The objective is actually to move this end effector A to make a diamond shape like this. Then we can use RC as well to control the voltage from motor A and motor B. And how the RC is structured? There are 2 types of RC here. And the first is it's called a generic repetitive control systems, and the second one is plug-in repetitive control system. So for a generic repetitive control system, it's placed exactly inside the feedback here, and while plug-in, it's in a plug-in manner. For instance, we have like a feedback control system with a conventional CZ, but after that we are going to add this RC. That's why we call as plug-in repetitive control systems. And this RC actually composed of 2 parts. The first one is internal model here, and then the second part is LZ, is we call as a learning function. Some people also call as a compensator. So for the so I separate between signal and system in this RC configuration, but I would like to highlight the system here. And for the system in this RC configuration, we need to know about the plant model. We need to design the LZ, the learning function or compensator. We need to know the conventional controller. Conventional control here may be PI or PID control, and also we need to design a QZ, a low pass filter here as part of the RC. And what is the formula of RC? There are two. The first RC or the conventional RC is actually has this form. So it has internal model here and LZ. This internal model here without a Q filter, and the second model is actually called as modified RC because we put a Q filter here. So this is the later development from the first model of RC. So we put a Q filter here, QZ, and here. When the aim is to improve robustness and to improve the stability. So what's the parameter in RC? So we have the learning function here LZ, and also we have n. The order n is actually the number of samples per period. So for instance, we have a periodic reference. So we can calculate n as the number of samples per reference periods, and TR is period of the reference. Also, we can also specify a TD or the period of disturbance. And this is the RC control law. And the RC control law here, we can see that to generate the current RC signal, actually we need the n previous samples of RC signal, also and previous sample of the error signal multiplied by the learning functions. And about the stability condition, to have RC stable, we need to have a stable plan here, and also we need to satisfy this condition that the norm infinity of 1 minus LZ PZ has to be less than 1. For plug-in, we have a different stability condition. It has to be PS is stable, and number 2 is that 1 minus LZ PS norm infinity of 1 minus LZ PSZ has to be less than 1. So PZ here is, for generic RC, PZ is plant model, while PSZ is actually the closed loop transfer function. So it's after multiply. It's multiplied by the conventional controller and then divided by 1 plus PZ and CZ. And the key things, it's the general assumption of RC, that the assumption is that the actual, this has to be actual, that the actual reference period is constant, and also the plant model PZ is also constant. And how to design RC? To design RC, actually we need to design the internal model, and also we need to design the learning function. The internal model design has to target the reference or disturbance frequency, and also this learning function is designed to satisfy these stability conditions. And the general design of LZ or learning function is the inverse of the plan. This is for general RC, while for plug-in RC, the general design of LZ is the inverse of the stabilized plan. So there are two key designs for RC. First is we design the internal model, and the second one is we design the learning function or the learning function or compensator to satisfy the stability conditions. Here, I will discuss about the internal model design. Like I mentioned before, there are two key design. First is the internal model design, and the second one is the learning function design. And what is the internal model design? The internal model design is like we trying to include the model of reference or disturbance inside the controller. So this is the form of internal model transfer function. So we have SDZ as actually a set of delays. For example number one is general RC. General RC we have SDZ as Z power by minus n, and we have this kind of internal model. And if we plot the pole zero map, we will have this kind of mapping. So if we have this internal model, then we'll have a poles located at the unit circle. So it's located actually at the unit circle. That's why this general RC is marginally stable, because it's in the border between stable and unstable. And this general RC is used for tracking subsignal, can be used for tracking subsignal with a frequency. For instance, this is the frequency of the reference and also its harmonics until n over 2 harmonics. So the frequency that can be tracked or cancelled is fundamental frequency, its harmonics until n over 2 harmonics. So that's for general RC. Then the second model is modified RC. We add the Q filter here, or a zero phase low pass filter, in order to improve the robustness, especially on the high frequency component. So we have here a high frequency component is like a put inside the unit circle. So before we have exactly at the unit circle, but here we have the high frequency component is inside the unit circle. So the drawback is that with this model we get a robustness. However, we sacrifice high frequency components, so the tracking accuracy at high frequency is not as accurate as the general RC. So here we can track or reject a frequency, reference frequency or disturbance frequency with frequency fundamental and its harmonic less than or smaller than the bandwidth frequency of the Q filter. So this is the second model of the internal model. The third model is odd harmonics order RC. So the SDZ is in this form, and we have before we have the order as minus n, but here we have the order as minus n over 2 is half from the previous model. And this kind of model is usually used in power application because it's only cancel the odd harmonics component. So this only track or cancel the odd harmonics component. Here we have a fundamental frequency and also odd harmonics, so 3, 5, 7, and etc. So that's the odd harmonics RC. The fourth one is low order RC. This low order RC has a low order because before we have the order of RC as minus n and also minus n over 2, but here we have low order. We have minus 2 for a single frequency. It depends on how many frequency we are targeting. If we have 2 frequency, then we are going to have 4 order. So this is for a single frequency. For 2 frequency, then we'll have 4. For 3, we have a 6. So this is an example. Those when we are targeting 3 frequencies. So frequency 1 is 5, frequency 2 is 12, and frequency 3 is 32. For a single frequency, we'll have a second order. So for 3 frequency, then we'll have just 6 order of RC. So this is actually to track or reject a selected sinusoidal frequency. So it's a selected. So different with previously that targeting a fundamental frequency and its harmonic, but this one is only a selected frequency. Next is the next model is multiperiod RC. So we are trying, let's say, for tracking and rejection for the same time, but it has a fundamental frequency more than 1. So for instance, I would like to track a 1 Hz and also to reject to reject the disturbance at 1.5 hertz, then we need to use these multi-period repetitive controls. So here that for example here that we have two fundamental frequencies, and we can reject this is the first fundamental frequency and its harmonic, and also we can reject the second fundamental frequency and its harmonics. That's for multi-period RC. However, what if the period of reference or disturbance is varying or is changing? So it's not exactly what we know before. Is the generic, modified, odd harmonics, low order, or multi-periods can handle that? The answer is not. When we have this kind of variation, then the number of samples per period will vary as well. This variation is affecting the tracking accuracy. The tracking accuracy is exactly significantly degraded. And another problem is, what if the plan model or the stabilized plan is non-minimum phase plan? Non-minimum phase plan means that it has unstable zero. When we do inverse, it will be unstable. And the generic learning function, which is the inverse model, is will result in unstable controller. And how to compensate that is, for the first problem is about the period variation. There are two approach. The first approach is we are using a high order RC, and the second approach is using adaptive RC. But I'm not going to discuss adaptive RC here. I'm going to discuss high order RC. So high order RC here it actually has a fixed controller parameters, and I will show how the configuration of this high order RC. And the solution for the second problem, what if the plan is non-minimum phase? The approach here is I'm proposing a new learning function design, and it has a stable and causal form. So the design objective here that I would like to explain is how to design high order repetitive controls to be robust against the period variations, and also how to design the learning function LZ to handle both minimum and non-minimum phase plans. So this is the structure of high order repetitive control system. So the structure here is also in a plug-in manner. Here we have a plug-in, and we have a high order repetitive control system as high order repetitive control as HZ, and we have a conventional control CZ and a plan PZ. And this is the transfer function of high order repetitive control. So we still use this QZ or the low pass filter, but here we have a DZ, and a DZ is in this form, and it's different with the previous structure that a DZ actually here is DZ. Here is DZ. Yeah, DZ is structure of there are many series of delays, and there are weights as well here, and the weight has to satisfy this condition. Why this high order we can call also high order internal model can be a solution when there is a period variation. So because when we plot the magnitude response of high order repetitive control here, it has of course higher peak and the nominal frequency, but also it has a higher gain here and the neighboring frequencies. So for instance here 10 hertz, it has a higher gain, let's say, and the value near that 10 hertz. So comparing to the generic RC, so generic RC is is the one with m equal to 1. Here m equal to 1, so this is the red line here, that it has a very a very short width. Then it means that it has it doesn't have performance to track or reject at the neighboring frequency. That's why high order repetitive control will give a better tracking accuracy. And how to design this high order repetitive control? Actually, we need to get characteristic equations, and also we need to derive the HORC stability conditions. So we have another. So we have here stability condition. It's different with the previous generic RC. So if we have the stability condition here, that we know this PSZ or the stabilized spline, we know the QZ or the low pass filter. We can determine that. We know the DZs. We also can determine that. And how about LZ, the learning function? How to obtain the learning function here? So I propose a design method to obtain the learning function that works for both minimum and non-minimum phase plan, but maybe I'm not going to go through the step one by one. But the idea is how to get the stable form of learning function. So I'm using a stable form here, stable form compensator here, and then I'm using the optimization to obtain this parameter B0, B1, BL, and A1, A2, and AL. And this A1, A2, and AL becomes a constraint here. So to make it stable, it has to be between -1 to 1. So to ensure that the result, the resulted learning function will be stable. This is the simulation results. So the simulation result is for a non-minimum phase plan. So we have this minimum phase plan. It's non-minimum because it has unstable zero. So this numerator actually has unstable zero. So if we are using the inverse of the stabilized plan, it's going to be unstable. That's why I'm using the proposed methods. Then using a second order LZ, so I need to find parameters B0, B1, B2, and A1 and A2, and using optimization MATLAB toolbox. And I obtain these parameters, I obtain these learning functions. And if we plot the magnitude response of this learning function and also the stabilized spline, that the magnitude response of learning function is actually in vice versa, it's also canceling. So this is the magnitude response of the red one. The red one is the magnitude response of the learning function, and the blue one is the magnitude response of the stabilized spline. And it's trying to cancel, even it's not exactly canceling. And how about the phase response? The phase response is also about to cancel the phase response of the stabilized spline. We have the blue one is the phase response of the stabilized plan, and the red one is the phase response of the learning functions. And this is the simulation result. So we have I'm trying to compare between the general RC and the high order RC here. So we have two control laws here, and for the first, let's say if we have that the reference period is exactly 1 second. So then both RC and high order repetitive control is able to, this is the tracking, are able to get a zero error. But if we can see that the transient response of RC here, the red one is RC, the general or the conventional RC is faster than the high order RC. It can be understood because the high order RC you need many sets of delays, like we see that there are serial delays with the weight. That's why RC here has a faster transient response compared to HORC. However, when we change the reference period, for instance, it slightly changed, slightly reduced to 0.975, then the tracking error is significantly big here. This is the red one is the tracking error for RC, while the blue one is the tracking error for HORC for these reference periods. So the tracking accuracy is significantly degraded for conventional RC when the period variation is happens. And when we try to increase the reference period, it slightly increased to 1.025, and we have the same result, that the generic RC has a bigger tracking error here. How about the minimum phase plan? I'm try to what we call to validate in the real-time experiment using a cube servo here. This cube servo is actually minimum phase plan, and it's trying to control the positions. So theta is the position, and Vs is the voltage. And using the optimization, and I end up with these learning functions. So this is the tracking output of the tracking output of high order repetitive controls, and the second one is the tracking output of generic RC or conventional RC at the nominal period 1 second. So again, it's able to track to accurately follow or accurately track the reference, and we can see that the transient response of conventional RC is better or faster than the high order RC. Then if I change the reference period to 1.025, here's the output, the tracking output of the high order RC, and the second one is tracking output of the conventional RC, and we can see that here the peak of the RC is smaller than the reference peak here. So like I said before, the tracking performance is significantly degraded when there is a slight period variation. The similar result is also happen when we change the reference period into 0.975, and we can see instead a smaller peak. It has for the conventional RC, it has a larger peak compared to the reference one. But for high order, we can see that it can accurately follow the reference signal. So that's about the high order repetitive control systems here. And the next is I would like to describe about how to integrate between a sliding mode and repetitive control, because that's two different, we can say powerful control methods. But how to integrate those two control methods, and what we are trying to achieve by integrating those two control methods. So for instance, we have a problem here that we have a disturbance, we have a periodic disturbance, we have with several fundamental frequency, and for instance that we are trying to track a reference signal with several fundamental frequency, and also in the plan, also it's subject to uncertainty, parameter variation, and etc. And the case when there are many fundamental frequency can appears on electromechanical system, hard drives, and power inverter. So that's why we need to trying to combine the sliding mode and repetitive controls. And the objective here is trying to the first objective is to track the reference signal RK accurately, and also to cancel the effect of disturbance WK. And also we are trying to achieve the transient response and also robust against plan variation. fast transient response here is an important issue, because like I mentioned before, that RC, if there are one period delay on RC, that actually makes the transient response is pretty slow. For instance here, so even for the generic RC, that there are about a one period slow transient response here in the red one, because there is one period delay here. And what's the solution? What's the approach can be used? And I'm proposing a name as multi-period sliding mode repetitive controls. It's actually combining the features of multi-period RC and also the sliding mode control. Here, the design is in discrete time approach. I think we know before about the sliding mode control, and it's a nonlinear control based on switching function. It can provide a fast response and robust to model uncertainty and disturbance. So now we have SMC, which is a nonlinear control, while RC before is linear, and how to combine that. And this SMC is also a well-established control method. It has been used in many applications. And well, in this case, I'm using a discrete time approach, and how to design the SMC. I mean, SMC without the RC. So the design step is actually, and the general design step actually, we need to determine the sliding function SK, and such that the sliding mode is in switching plane SK is equal to 0 is stable, and then because the design is in discrete time, then the second step is determine the reaching low. The reaching low is the difference between SK and SK minus 1 that directly dictates the dynamic of the sliding function. And then after that, we synthesize the sliding mode control law based on the reaching law and also on the non-model of the plan. And how to design, how to combine this RC and sliding mode control? Is that just we adding URC with USMCK? Can it work? So I don't think so. There is a design step to do that. And the next question is, which stability condition is used? For RC, we use a stability condition in frequency domain. And this is linear control, while it's SMC is a nonlinear control. We can use this frequency domain approach. And in SMC, using a time domain reaching conditions. Then which one stability condition is used? Then I'm going to explain in the next slides. So for instance, if we consider this linear time invariant model with output disturbance here, so I'm considering a single input, single output model with the output disturbance, and this output disturbance may have several fundamental frequency, and BZ and AZ is actually the BZ is the numerator and denominator, and D is actually the non-delay steps. And the question is how to generate UK or UZ here to achieve accurate tracking of multiple periods reference signal, also doing a good rejection of multiple period disturbance, also provide fast transient response, also robust against parametric variation, for instance, in the numerator or denominator parts. Then here's the design steps to combine the sliding mode and repetitive controls. The first, we need to formulate the tracking error dynamics here. So this is the difference between the reference and the tracking output. And after that, then we substitute this YK with the plan models. Then we have this error dynamics. We are going to use this error dynamics in the next steps. And I think the key as well here, the key important thing is to determine the sliding function and reaching low. And there are many choices about the how to choose the sliding function and reaching low. In this case, I'm just using a linear sliding function here that I pick polynomial CZ as Hurwitz polynomial or stable polynomial. And the reaching low here, I'm using I think also this is a generic reaching low with a smoothing function SFK. And here in the smoothing function using saturation functions. Then we need to pick, or we need to choose the internal model of RC. So the internal model of RC that we are going to use is multiperiod RC. So from my explanation before is the model number 5. So we are going to use this model, and we are interested only in the denominator of RC here. We are going to use this part. So we are going this denominator parts. Then we can represent this denominator of RC model here as IMZ, which is equal to 1 minus AZ, and AZ is actually represented in this equations. So then after that we synthesize that multi-period sliding mode repetitive control here, and there is a step-by-step how to synthesize that, but just skip it for simplicity. So actually we end up this kind of multi-period sliding mode repetitive control law here, where we find a new transfer function here, mz, which mz is actually in the polynomial cz multiplied by numerator bz divided by denominator az. And if we can see, actually there are two parts here. And the first part here actually it's RC part, and the two last part here is the sliding mode control part. Then from that control law, actually we can plot, or we can we can plot the configuration of sliding mode repetitive control here. So we'll have this what we call we have this structure. So we have the tracking error here, and then the transfer function cz, and then we have sliding function here, and the top part is actually RC, and the bottom part is SMC. And the question is the control law is implementable, because there are there are some question here. For instance, we have a Z powered by D, it's positive. Is it implementable because it's non-causal? And also is the inverse of M is stable or not? So there are two important remarks here, because the term AZ here indicates that multiple delays with a different length arranged in parallel, and the non-causal term ZZ is applicable because it's multiplied by EZ. And the inverse of MZ is also stable, because we use an LTI system with minimum phase system, which means that its inverse is also stable. But for non-minimum phase, we are going to have a different design methods. We can use this one. And stability analysis. Stability analysis. Now we are going to use because now it's become nonlinear control, because we combine RC and SMC, means that it's end up with a nonlinear control. That's why we are going to use the stability of SMC. So we are going to use this reaching condition to check whether the proposed control law is guarantee the stability or not. But I'm not going to show the stability proving here. Let's see in the simulation result for this case. So let's say we have a model quasar servo here with the output disturbance. This is the discrete model, and then I pick the sliding the polynomial CZ, and I choose some parameter for the SMC here, and then the EZ is in this form, and we have the transfer function of inverse of MZ is like this. Then finally we can construct the control law of control law of sliding mode repetitive control here. In this case, let's say we are going to reject, we are going to track a periodic sinusoidal reference signal, and also we are going to reject a disturbance which has two fundamental frequency here. So our two fundamental periods. So the period 1 is 0.8 here, and the period number 2 is 1 second. So that's why we have two fundamental frequencies. And we need to calculate the number of samples for a period 1. We need to calculate also the number of samples for period 2. We have 160 and also 20. So this is the disturbance that we are going to cancel. This is the simulation result. So on the left side, we have the simulation result for a sliding mode repetitive control, and the right side is for RC. So we can see that using the sliding mode here, it's improved the transients compared to the conventional RC. And also the peaks error is also smaller than the RC, because when the RC is still what we call still learning, because there is a one large delay on RC, then the sliding mode part will handle that. That's why it gives it gives a response or faster response compared to the conventional RC. And what if we trying to vary in the plant parameters? For instance, we change by 2.5. The second we change by 5%. And for sliding mode repetitive control here, the tracking error here, we can see that compared to the previous one without the plant variations, the transient response is slower. However, it's still stable here. While RC here also show that the transient response is also slower and also still stable, but the peak is larger compared to sliding mode. What if we increase to 5%? So if we increase to 5%, we see that the sliding mode repetitive control, the tracking error here, we can see that it's the transient response, it's getting slower, yes, compared to the 2.5% variations, but it's still stable. While RC here, it's getting slower, but also it's also unstable. It's diverged. It's diverged. It's go unstable. But I think this is it can be understood. It can be understood because RC is like I mentioned before that RC is marginally stable, which that has the pole exactly at the unit circle, which means that it's easily get unstable if there is a plant variations. I think that's for SMRC. Then I would like to close with the conclusion. So there are two key design of repetitive control. The first one, we need to pick or we need to design the internal model. We need to choose, which internal model that that suit with our with our preference. For instance, what kind of signal we would like to track, what kind of signal we would like to reject, and the frequency components in this signal. And then the key design number 2 is we need to design the learning function or the compensator. The learning function is part of RC that can stabilize the whole RC systems. And like there are 5, and now there are 6 internal model design. There are 6 internal model types. The first one is general RC, modified RC, harmonic RC, low order RC, multiperiod RC, and the last one that is the high order RC. RC itself has primary drawbacks. For the first one is sensitive to period variations, slow transient response, and also not robust against plant uncertainty. However, high order RC can be used to compensate slight. This is a slight period variation. However, if there is extreme change in the period variation, high order RC cannot handle that. So high order RC can be used to compensate a slight period variation, and the learning function is designed based on optimization that used to stabilize both minimum and non-minimum phase systems. And the other control method, sliding mode control, can be integrated to RC to achieve tracking and rejection simultaneously, fast transient response, and also robust against plant parameters variations. Then the the sliding mode repetitive control law needs to satisfy the sliding mode reaching condition, because when we integrate a sliding mode control to RC, now we have a nonlinear control because we already added the nonlinear part. That's why we cannot use the stability condition from RC, but we use the stability condition of sliding mode control. I think that's all for my presentation. So please welcome if there is any feedback, any comments. So I will return the session to Hai Wang.
Thanks, Eddie. Thank you very much for giving us the very excellent presentation regarding sliding modes, repetitive control systems. Actually, I've done almost 10 years research on sliding modes, control theory, and applications.
Okay.
I think this. By combining sliding mode control theory and repetitive control methodology together, would be a very the useful techniques for industrial applications. And based on your presentation, I have seen that the combination of sliding mode control and repetitive control design can definitely provide us a very accurate tracking performance, as well as good rejection capability of the control systems, as well as fast transient response and robustness against parametric uncertainties and disturbances. Yeah, and I believe this could be a very good candidate for our industrial and mechatronic applications. So, any questions from our audience? Please feel free to ask. Thank you.
Hello, Dr. Eddie.
Yes, hello.
Firstly, many thanks for your excellent speech. And I have some problems. Firstly, I want to know what's the difference between repetitive control and the normal control task. Because I think repetitive control is just the signal is like a sinusoidal signal, which is just like one case of our normal control task. So I don't know why it separate from our normal control task.
Okay, that's okay. Sorry, may I know your names?
Yoho.
Okay. Okay, thanks. I think that's a good question. What's the difference with the normal control methods? Actually, we can classify this repetitive control as predictive control method because, well, it's using the previous one steps cycle to generate the control signal, and this repetitive control is working good for periodic or repetitive signal, but for non-repetitive control signal it's not good. So it's different with the for instance PID control. For instance we are using PID to track step or to track the periodic signal. There will be a overshoot and also transient, and then until it gets a settling time. But by using this RC, because it's trying to use the previous cycle information, we can get the exact or accurate tracking output, but with, of course, if the reference or the disturbance, or if the reference is a periodic signal. So RC works well if the reference is periodic signal.
Okay, okay. Okay, I got this. And I have another problem. I don't know
Yes.
what's the function of your learning function.
Okay.
Yeah, I think in perhaps slide 10.
At 10. This one.
Perhaps 9. Yeah, there is a learning function. I don't know it's a real function.
This one.
Yeah.
This learning function is actually a transfer function here, and some said also we can. Some people also call as compensator because this function is trying to stabilize the whole closed loop systems. Because without this learning function, only this internal model, then the whole closed loop system will not be stable. That's why this we need this part, and the general form of this learning function is an inverse of the plan. It's trying to cancel the plan. Okay, that's why we can get the exact output here if we give the reference here. So this learning function actually what we call it's a transfer functions that trying to stabilize the whole closed loop systems. And maybe I would like to show you again the learning part is actually here. So it's trying to study from the what we call one cycle before that we can get what we call the accurate tracking. So it's different with the conventional control like PI or PID. So when we try to track, for instance, this a square signal here, repetitive square signal here, if we use PID, still we'll get the what we call there's overshoot and also and what we call rise time and etc. until it got settled. But with RC, we can exactly track this kind of subsignal. Yeah, I think that makes difference with the conventional controller, but the RC works for periodic signal. If not periodic, it's not going to work.
Okay, so it's a control law, right? The learning function itself is a control law.
Yes.
Okay, so is this time delay control method?
Yeah. Yeah, it's like a time delay control method, but the delay here is on the control signal as control signal and also in the tracking error here. Yeah.
Okay. And the last question. As far as I know, sliding mode control itself is already capable of controlling disturbance and control that and offer some robust control. And so, is it necessary to? I mean, the merit of such combination of SMC and RC and repetitive control, right?
Yeah, but there is I think a drawback as well. If we have like a periodic reference signal like this, I think SMC cannot achieve such high accuracy to track something like this. That's why we need the RC to do that. I mean, in my experience, I mean to track the high frequency, something like this, a periodic, and it's also good for tracking. But for achieve a high accuracy tracking repetitive signal, I think SMC is not as good as RC. That's why we try combine RC and SMC. And in this case, SMC is trying to provide the fast transient response and robustness, because RC here is marginally stable, means that it's easy to go unstable, especially when there is a change in plant variations. In there is a change in plant. Yes.
Okay. Yes. It can be seen that the control precision has been improved. Thank you very much for your answers. That's all my question.
Okay, thank you for the questions.
Thank you, Eddie. Thank you, Yoho. So, any more questions from our audience? Because I know some of the audiences should, have done many researches on dynamo control theory and applications. Yeah.
It's almost evening, I guess. There is it right?
Yeah. So, any more questions?
Hello, Professor. Can you hear me?
Yes, I can
Hello.
hear you. Yes. Yeah, can you hear me too?
Hello. Yes, I can hear you. Hello, I'm Mao. I
Mao,
have
okay.
interest in the
Uh,
describe the system. You know, at the beginning, you talk about the describe process of the system. Uh, you,
sorry, I
I
cannot
mean,
hear you.
okay. At the beginning, you talk about the describe the system by using some by using some method. We
Mm,
also get a continuous system by using
mm,
physical equations and mathematic ways.
mm,
But we need to transfer it in the state, the digital control system. I mean, we need to actually,
mm.
the pair we used in the system is fixed, but in the actually they are variable in the uh, uh, I want to know how do you tackle this problem in your system.
Uh,
In the, for example, in
sorry, I couldn't
and
hear
K
you.
and L, yes. Uh, okay, can you hear me?
Yeah, but your voice is sometimes on off and on off. Yeah, now it's better.
Okay, sorry. The internet is not very good in my
Sorry, you
in my
asking about
area.
the
My question.
you asking about discrete time conversion here, like the slide that I saw you at this time, or
Yes, yes.
yeah, because there are many discretization method to get the to convert from the continuous to discrete time, but
Yes.
there are many methods of that, but I'm not going into deep which one, but yeah. Mm. There
Okay,
are
okay. I
several,
know, I know.
like a
Just
several
use.
other, like a Tastin method and several other methods. Yeah.
Okay, okay. I got it. Thank you, thank you.
Uh,
Possibly they have some,
Thank you. I have no
communication
question. Thank you.
problems in most network. So possibly after this, presentation, most can send an email to, Eddie for further, questions. All right.
yes, you can tell me.
Okay.
Yeah.
Yeah. And any more questions
Okay. Thank
from
you very
our
much.
Yeah.
audience? Yep. All right. So Eddie, I have one question.
Okay.
Yes. Because now you are using the slightly more repetitive control for applications, and do you have any idea about the the change of the sampling frequency in your control methods, and is any effect for the application? Yeah, for different applications. Yeah.
Even the sampling time.
Yes, yeah, the sampling time, because for sometimes for the
Yeah.
practical application the sampling period is not that small. It depends on the bandwidth of the whole closed loop system. So in this case, does it affect the closed loop control performance of your system? Yeah.
Yeah, this the sampling time how to choose the sampling time is about tricky as well. That's why, in my case, I'm not what we call going into deep about the sampling time, but I'm trying to pick the. I think this is just the small sampling time as possible, as small as possible, but. Because I think the issue about sampling time is quite tricky for the SMC because it can affect on the other things like chattering and etc. And also I'm carefully also tuning the what we call the some SMC path parameters. Yes.
Okay.
There are no exact rule about how to choose, but it's careful actually.
Okay.
That's
All right.
what I can say about the choosing the sampling times. A different application might a different sampling time. It can
Okay.
be small sampling time doesn't guarantee and yeah.
All right. Yeah. Because sometimes if you change the sampling time, the whole the control performance should be affected. Yeah. So in this case, we have to be very carefully select the sampling time. Yeah. And in the simulation cases, so is any smallest like the minimum sampling time when you do the simulation?
I'm not trying to what we call trying to find the minimum one, but in RC as well, the sampling time is affected the number of n here and the number of samples here. If we pick or we choose the sampling time too small, then the number of samples here per period n is also bigger as well. It's also to be careful. So because it's related to the delay size.
Yes.
And what what I have done before, I pick the sampling time. Yeah, I don't mention about the sampling time is about 0.005 seconds.
Yes, I've seen that. Yes.
Yeah.
Okay. All right. Yeah. Thank you, Eddie. Yeah. So, any more questions from our audience?
Hi, Eddie.
Yes. Hi.
Hi, my name is Stone, and I'm from Melbourne Uni. I've just graduated from the Department of Mechanical Engineering.
Okay.
And I'm quite interested in the topics of control theories and applications. And thanks for your speech today. And I've just seen your model is it quantum servo model, like a vertical bar or something like? Because I have used the quantum arrow model to use for LQR control applications. And for your for this question, I think you could just use some like control effort. Sometimes it's just saturated, so your control, like sometimes it's just saturated, so you won't get performance you desired. And also for the question high set, I think for your model, because the model is linear, it's so the sampling time is just you are trying to seeking the maximum sampling time, because sometimes it's just control effort, and your it takes some control effort to do that, because you are using discrete time model, right?
Yeah.
So you are converting from analog to digital signals. So sometimes, what method did you use? Like testing or like just the conversion?
Like, there are several conversion methods like a zero order Hall method and then testing. I think I picked the zero order Hall one. I think that the full ones that I'm using, and you also asked about the Quanser. Yeah, that's from Quanser. I think Quanser there are cube servo and also other SRV SRV motor. This cube servo comes with the, I think, what we call a DAQ as well. So while the SRV one is also, we need the Spirit data acquisition board. So this cube one is just we can plug to the computer. And also, yeah, the control effort is also an issue here because there is a limitation on the control signal that need to generate. That's why sometimes the control effort is also too high, and also it's deteriorate the performance. And in this case, that's why the use of filter is here. It's quite important here. That's why if and the Q filter here is quite helping in actually to suppress the control signal, because if the control signal is too high, it will be saturated. But they use this Q filter here, then because RC here is pretty sensitive to any change. That's why a small change, it will trigger a high control effort. And by using the low pass Q filter here, it will helps RC to generate more, a smaller control effort, but with the performance is still good. But again, the tracking accuracy, especially in the high frequency, is degraded. But sometimes we don't need the high frequency component. Sometimes, yeah. Yeah, I think that's can answer your questions.
I just saw your like AD conversion, so I think you can just try testing instead of the hold, because I have tried some experiment on like the Quantum arrow.
Model. So testing gives a better, because I'm not trying one by one. I just use the default the default what they call a conversion method. Yeah.
Yes. Also, you can use something like architecture like parallel iterative learning architecture to improve your performance, I think.
Okay.
Because you are using something like compensation to compensate the plant model. So right. I think sometimes you can use more like adaptive control laws. I think it's just I don't have like that much question, but I just think I just have some thoughts on your project.
Okay, nice. Testing, yeah. And then, do you mean iterative learning control or iterative? What do you mean by iterative?
Pardon?
Do you mean iterative learning control?
Iterative learning, so it's like ILC.
Okay. I heard about that. So ILC is another, I think we can call another control method that has a almost similar performance to RC.
Yeah, because I saw the architecture is quite similar. So
yes.
So
that's right.
Thank you.
Thank you, Eddie. Thank you, Dun. And I think if we can combine adaptive control or iterative learning control methodology with the sliding mode repetitive control, that would be give us a new research directions. That would be good. Yeah, thank you. And okay, I think is all there. And lastly, many thanks for Eddie's excellent presentations today, and I believe we have all enjoyed today's webinar. So finally, thanks very much for Eddie, and thanks for everyone's attendance today. And I'm looking forward to your attendance in our next seminar. Thank you. And keep healthy and stay safe. Thank you.
Thank you, and keep in touch.
Yeah, keep in touch. See you. Bye.